two root finding methods so far. One is bisection method, which literally just finds a bracket or an interval where I have a positive and a negative value of a function that I'm looking the root for. Root is a value that zeroes out the function. And then I have to say, okay, if this function is continuous, then I will have to meet a zero somewhere in between those two ends. So it just ends up halving the interval and figuring out which side is the correct bracket as it goes. And it stops when that interval is small enough or the width is small enough. Okay. We decide the width. If you are not asked for the width, that means that the miracle method underneath has decided it for you. Okay? So it's pretty simple algorithm the way they go. Now, this method always works, but it's not always the fastest because it's never actually asking itself, well, what are, other than just looking at positive and negative, what are the values of this function? Could I get to that root a little sooner? And false position attempts to do that. It's not always good at it, but in many occasions it is faster. So what it does, it says, okay, I'm going to temporarily approximate my function, however complicated it might be, with a straight line in between these two endpoints of the bracket. And then I'm just going to find the root of that linearization. Okay? And you can basically compare these two triangles and figure out that this has to be true. And out of it, you can actually back out what XR should be. So instead of just taking a midpoint of an interval, this is what it's going to take. Okay? And at every point, it's still going to check whether my interval is a bracket afterwards, and that should work fine. Now, if you remember at the end of the last class, I had, for some reason, there was a little infinitely running loop or whatever it was. I cannot figure out what was wrong because when I got to my office, it was working just fine. So it was some temporary mishap of the, is this the, yes, so this is the false position method. I'm going to now execute them all. So let's just briefly review what we have been doing so far. So we've been working on that parachute problem, where we're actually looking for a drag coefficient C. Or, no, and then we replaced it, actually, this is not a parachute problem anymore. We replaced it with a polynomial. Specific polynomial function. And this polynomial is, here it's written in terms of c, so f of c is c cubed minus 5c squared plus c plus 2.5. Okay? And first thing that you do is you investigate it graphically and just look at how it looks like on some interval. And for this one, we actually see that there is 3 roots that I could be looking for. So in order to use either bisection method or false position, you have to bracket a root that you want to. You're always searching for one root at a time. Okay? So you bracket one root. Now technically, I can do a bracket -2 to 6. Okay? And then if I was doing a bisection method and I ran -2 to 6, what would be my next interval based on bisection method? What is midpoint? Between -2 and 6, what is the midpoint? 2, right? Then what does bisection method do? It looks at this, and what is it going to look at? Look at f of this, -2, and f of 2. When I multiply them, is that positive or negative? Negative. This one's negative times this one is negative, so multiplication is positive, right? Both are negative. And therefore, this is not a good bracket. yet I actually have 2 roots in there. Okay. And this is because we actually had initially 3 to begin with inside of this bracket. And then I'm going to investigate f of 2 and f of 6. This is negative, the other one is positive. Good, that's going to be my next bracket. So if I actually choose minus 2, 6 as a starting interval for this function that actually brackets more than just one root, okay, the root that I will actually ultimately find is the one that is close to 5. Okay. So it is an algorithm. It's not foolproof. It's not knowledgeable in everything, right? Algorithm just does what it does. Okay. Now, if I really wanted to find this root over here between minus 2 and 0, then minus 2 and 0 is my bracket. Okay? So that is one of the pitfalls of these methods. You can find the bracket. You don't know necessarily always how many roots you have in between that bracket, especially if you're just like jotting down the values and using a calculator to find them. Okay? But you will find a root. Okay? And sometimes in some weirder situations, you might actually not necessarily be able to find it. Okay? So it would still figure out, let's say that the 2 was actually a positive value, then it would actually go to this side and probably find one of these. Okay? Questions? So that is the bisection method. And we have actually programmed it as a function, so I can actually try it out. So actually, let's try. And I have programmed it not only as a function, but also that I can, if I wanted to, modify what is the width of what is my stopping criteria, right? The stopping width that I'm happy with. So that can be changed. So let's actually try to run it with minus 2 and 6. So if I did indeed with minus 2 and 6, I would come up with this root that is close to 5. Okay? Same as running it with 4 and 6. Now with false position method, what is really changed is just one line, and that is how am I picking my midpoint, what used to be a midpoint. Now it's just going to be computed differently, and that different comes from this formula. So if somebody gives you a formula, even if you don't understand what the method does, you can actually easily modify to get this. Okay? So what we now replaced, instead of a midpoint, we take xr as x of u minus f of xu times xl minus xu over f of xl minus f of xu. And when I execute that, let's see. Do I have any printouts? So both of the methods will actually zoom in on a pretty, so here I'm returning only one value. Both of the methods will come up with a pretty similar root. Okay? I can. And again, the only thing that has been changed is how I pick this iteration. Now, one thing when for some reason it didn't run during the last class, I actually put in my attempt to debug at the end of the class, I put in the iteration number. And this is actually a good idea always to do, just in case you are caught up in some sort of an odd problem, you'd like to catch it and not have an infinite loop. So you put an iteration counter in there, and you set up a maximum number of iterations here for all of the problems that we're going to deal with here. 10,000 is reasonable. So I'm running this loop both while this width of the interval is larger than what I'm looking for, and my iteration is less than maximum iteration. And here I have a specific, these are bracketed methods, so I have a specific interval, interval width. What is my stopping criterion? Could also be slightly changed to be more in tune or to be more comparable across different functions. So I could actually put here a relative error, okay? Not like, this is essentially an absolute error, okay? So instead of absolute error, I could divide by either value of xr or xu or xl, whichever one you pick actually in this particular case, making sure that none of those values is 0. Okay? And then I would just make sure that my relative error is less than some number. So this width is something that you can change. So basically one could, I'm just going to write down a note. So we can either run while width of the interval, or rather until width of the interval becomes small, which is in effect absolute value, absolute error in my iteration. Or we could compute relative error, which is better for comparison in between different functions. Okay, so I'm relative to the value of the root. And I'm thinking more in like, oh, is it 10% or 0.1% of the actual root? To have better comparisons in between different functions. So we will implement that in the further examples. There is no need here. So one thing that I don't, or many people don't like, is this, that I have to search for the bracket before I actually go and get, let me just, is better? There we go. This search for a bracket, okay? How about if we can investigate some methods that require only one guess before we actually start the method? And those are usually faster if they converge, but they have less, we can't always say that they will actually find the root. Okay? So you can relax this issue of having a bracket, okay, and just start from some value and go and try to search. However, you might not be guaranteed finding a solution at all. Okay, so let's look at one such method. This one is actually very simple to set up. It's called fixed point iteration, and it's great when it works, but it often doesn't. So let me explain how it works when it does. If I have my f of x is equal to 0, so let's say x squared plus x minus 1, I can algebraically rearrange it as x equals to whatever is the rest. Okay? So in this case, I leave x on one side and I put the rest on the other side. And there's no single way to do that. Okay? If I had just sine x, then I could just add x on both sides. Okay? In any event, let's just go with it. Let's say that we figured out how to formulate my problem f of x is equal to 0 as a problem x is equal to g of x. If I have that, then I just start from a guess, some sort of x0, and then I find my next guess, x1, as g of x0. And then on next iteration, x2 is g of x1. And then on next iteration, x3 is g of x3, 2, and so forth. So every time I have my next guess, k plus 1, it's g of the previous guess xk. So that way I just start from 1 and just keep going until I'm happy about the relative error between my two latest iterations. Okay? So that's kind of simple to set up. And the problem is that some of these arrangements may diverge. And in essence, let's say this is conceptually why it might diverge. So if you actually have, this is your f of x, okay, this is the root you're looking for. You're kind of breaking it up at various function f of x is equal to x, intersecting the rest of this function, right? So I'm looking at it geometrically. So I'm geometrically looking at this for this point, okay? Now, in case that my function g of x that I came up with actually has a very gentle slope, g prime of x is less than 1 in absolute value, I will then converge. Otherwise, and very quickly. Otherwise, I will not. Here is why. Let's say that I'm starting from x0, okay? My next iteration is g of x0, my x1 is g of x0, right? And let's say that this is my function g, so it's right here, okay? This is its value. Now I will actually walk myself to, if this is my g of x, and where this line is intersecting function y is equal to x, that's basically where my x1 is. Because for all of the points here, their x and y are the same. Okay, so if this is g of x0, then this is g of x0 here too. So this is my x1. And then I repeat that. So I find my g of x1, which is right here now. Okay, so my value of x2 is right here. And I keep going like that. I will basically kind of slide down to this intersection geometrically, and I will converge to my root. And that's all because this g of x has a very gentle slope. If g of x has slope that is not so gentle, okay, I will start with g of x, so for instance here, okay, this is my x0, this slope is not so gentle, so my g of x0 will send me right here, this is my x1. And then the g of x1, right here, will send me right here as x2. And I will keep actually spiraling away from the root that I need to be at, which is right here. So basically, if it's a gentle slope, g prime, g has a gentle slope if its g prime is less than 1, then I'm going to converge, otherwise I will not. So let's give it a try. Okay. So for this problem B, f of x is x to the 4 minus x minus 10 is equal to 0. Can you come up, let's say as a class first, come up with a couple of different versions of this function g? So I'm looking to reformulate x to the 4 minus x minus 10 is equal to 0. I'm looking to reformulate it into x is equal to g of x. So I'm wondering what is g. And there's multiple ways to do that. So can you come up with at least 2? X
to the 4 minus 10.
Okay. So this is my g of x, right? What is g prime? Okay. So if I'm around number 1, x is equal to 1, then this is going to be at least 4. Okay. So that's not likely going to converge in the neighborhood of number 1. Now, I don't know which precise neighborhood, but this is an example where it might converge if I get there. One simple way to see whether it's going to converge for any starting point is simply to try it out. So let's program and try it out. So this is so-called fixed point iteration. And my f of x is x to the 4 minus x minus 10. Is it minus or plus? Good. Okay. So trying out x is equal to g of x, which one is x to the 4 minus 10. So what is my iteration? My starting point, let's say that I start with 0. What is my next one? I'm going to call it x1. What is my next iteration? So I just want to compute it in terms of x0. So what is it in terms of x0? Okay, it's g of x0. Yeah? I'm programming. I wasn't actually looking for an actual number. so I start with xk. My next iteration is always, so I have x0. My x1 is g of x0. My x2 is g of x1, and so forth. Okay? So now I'd like to set up a loop to do that. This is just me writing it down. Okay? And I suggest that this is a good way. So you give yourself a starting point, initial guess, and compute the next one. Okay? But I want to do this in a loop. So what would I do in the loop? I gotta have a while in there. Okay? While some error is larger than some epsilon, I'm gonna give myself an epsilon. And I'm going to compute, for now, I'm just going to say, well, error is 1 to initialize it. Okay? Do what? Compute my next one. Error is my absolute value. I'll import NumPy. And what else do I need to do to actually advance this iteration? Change my x. So my x0 has to be updated. Okay? And that's it. So this is the way to program this. First, don't get stuck. First, give yourself initial guess. And then just say, well, what is x1 in terms of that initial guess? Okay. And then set up a loop to actually keep doing that and replace your initial guess. Yeah? Two things I wasn't careful with. I wasn't checking whether I'm dividing by 0 here. I could hit a 0, okay, in which case my error would be infinite. but it would probably just fix itself up in the next iteration, so it's not a huge deal. Okay. And one thing that I wasn't careful about is setting up that there's a very good chance this doesn't converge, right? So I would like to set up the maximum number of iterations. So I'm going to say maximum number of iterations is 10,000. This is iteration 0. And here, and iteration less than maximum iterations. So I'm going to increment iterations. I am making a point of writing this fully, but you can actually do this in Python just to shorten your writing. But I'm not here for the shortness of writing. I want it to be clear what it's saying. But if you want to shorten your writing, you can. Okay. So let's see where does this go. I'm going to, at the end, print my x1. Let's see the moment of truth. Nothing. Has it even entered while error larger than it? There's no star here.
We'll go up because mine has stars.
Ah, there you go. 10,000, it hasn't stopped. Should have been able to handle 10,000. Let's do 100. Okay. For some reason, it's just not doing anything, really.
Oh, did you report it? No.
Yes, I did. It didn't say an error, it just keeps running. It should at least print these X1s, and it's not. So something is stuck. I guess my computer, the moment it connects to this.
Mine's doing the same thing.
Doing the same thing?
Yeah.
Not even printing?
I'm changing everything as you change it. It's doing the same exact thing.
Step-by-step debugging. Okay, stop. Kernel. Unexpected indent, fine. Okay, so this one is fine. I'm going to limit myself to 5 iterations. All right. Something got unstuck without me actually doing anything. This is just 5 iterations. Is this converging? No. If I let it more iterations, it's going to suddenly decide it's infinity. So it's going to print my... Let's go to 10. And I don't know what was stuck with it, but now it's working. So try interrupting your kernel and sort of restarting it. So I think once it actually hits that infinity, something gets messed up. Because 10 iterations are not running. Ah, there they are.
Oh yeah, it's a lot.
I think what it gets stuck with is printing. It's trying to dump these huge numbers into the screen and cannot cope with that. That's what ends up being stuck.
I just deleted print, it's still stuck.
Then it's just looping. Then I have no explanation for what is browser doing. But it's this communication between when it gets into the infinite loop, it has trouble going back and forth. So it's requesting to print is a problematic thing because it's this large thing that just keeps growing. Okay? So this is not converging. Any other ideas? What is another thing that I could do here? How about I say x to the 4 is equal to x to the 10, and then x is actually x plus 10 to the power of 1 over 4. Why is that going to be better? I'm going to have a better chance when I do a derivative of this. I get 1 over 4, x plus 10 to 1 over 4 minus 1. There's a better chance of controlling the size of that than there is for this. Okay. So let's just give it a try. Without overanalyzing, let's just give it a try. So I'm going to replace this. This is not converging. And it's messing up my Jupyter notebook, and possibly yours as well. So in this case, my function g is x0 plus 10 to the power of 1 divided by 4. So I just changed my function g. So I will not make note of that here, or x is g of x, which is x plus 10 to the power of 1 over 4. Let's give it a try, and given my bad experiences previously, I'm going to limit myself to 5 iterations. Oh, okay. Getting somewhere. This is how you can see that it's actually starting to converge. So this one I could probably let go. And actually it's done after 4 iterations. These 2 iterations are close enough. Okay? So good steps when forming this is write down what is your next iteration, just compute 1 or 2, then form your while loop, and try to print first 5 values. Where does it go to see whether it's converging so you can fix up any errors. And maybe it's not an error, maybe it's simply method that is not converging.
Can you show the code that you
Mhm.
put through? Where you made some changes?
So if you're changing your G, all you change is this line that is recomputing the next. Okay? So that is the only change. The rest of the code, the moment you have the new iteration, you can recompute the error, okay? And you replace your previous iteration. And you increment iteration. This piece of code is kind of the same for most of the methods, right? Okay. And now I'm going to actually introduce what's the most famous method. And when it does converge, it's the fastest. That is so-called Newton or Newton-Raphson method. So what that method does conceptually is the following. It says, hey, this is my function f. Okay. I start from an iteration. I'm going to call it as xi here. And my next iteration will estimate the slope of the function at this point. That's f prime of xi. And it will simply see where does that slope intersect my point 0, my 0 value here. And that's my xi plus 1. If I actually look at this xi minus xi plus 1 and figure out this triangle, I'm going to get that my next iteration, xi plus 1, is xi minus f of xi divided by f prime of xi. The thing that I have to know about this function is I have to know both the function and its derivative and have it programmed for this to work. Okay? So if we were actually working with the method that I just had previously, over here, I can actually quickly reformat this into Newton's method. Okay. It's just that now these g primes don't apply. What I need is f prime of x, and I'm going to compute this within the code so I can work with it. And basically my next iteration, I'm going to write it down here before I program it. So my x1, I'm just going to work in terms of x1 and x0, is my previous one, x0, minus f of x0 divided by f prime of x0. This is basically what was done right here. Okay? So just translated it into my code values. And I already have the shell of my code from fixed point iteration. I'm going to reuse it. Okay? The only thing that I'm changing is this part. Okay? So it's x0 in this case minus f of x0, which I'm going to borrow from here, which actually I'm going to define functions to find f of x. It's x and I'm going to call it df of x as a derivative. X 4 times x cubed.
Is there a minus 1?
Yes, there is. That would be divergence right there. Okay? So basically when I program it, I just do x0 divided by df of x0. So I just reused the shell of the code I had before. It's really how do I define my next iteration? that I'm plugging in here. Okay. So for Newton's method, I have to have both f and derivative of f, which I programmed here. So if I were to use this for a different function, what I would change is this part where I define how I compute function and derivative of the function, right? So as you get the homework, basically you will just get various cases of this. So you will just kind of replace the key parts, but the shell of the code remains the same. Questions? Quick questions?
Scroll up.
And I don't know yet whether 0 actually works for this. It does.
Can you show the while loop?